13.2, Graphs and Level Curves. The graph of a function in two variables is a surface. As x and y change, the elevation z will change. Let's find the domain of this function. We must have all values under the radical to be either 0 or positive. That means only values contained by this circle of radius 2 centered at 0, 0 will be allowed. As your x and y coordinates change, elevation z changes. Let's fix a value of z. At a particular value of z, at a particular elevation, you will be given a level curve in the xy plane. Let your z values vary, always by the same unit. You end up with a contour map of the Mount Katahdin. When the curves are closely spaced, that means that we're having a rapid change in function values. If the curves are widely spaced, that means a slow change in function values. When the lines are close together, that means a steep elevation. When the lines are farther apart, that means a more gradual elevation change. Let's sketch the level curves of this function. We're going to vary z by 1 unit every time, starting at -2. Put that value into the equation and then simplify. Do that now. These are the equations I get. Each one of these equations is the equation of a parabola. So all of the level curves are parabolas. The only difference is the intercept. Here are our level curves. Each one of those curves represents a different elevation of our surface. Suppose that on a particular day the fraction of students on campus infected with flu is R. So if you encounter a student, there's a probability of R that they will have the flu. Let's say you have N encounters. This function P is the probability that you will meet with somebody who is infected with the flu. What would the level curves look like? Each one of these level curves corresponds to a particular probability. How about this electric potential function? First, notice that the domain is all values except 0, 0 and 1, 0. This is its surface and its level curves. Notice the absence at 0, 0 and 1, 0. Let's find the domain of this function of 3 variables. Again, underneath the radical, it has to be either positive or 0. And so the domain is the closed ball of radius 4 centered at the origin. How about this function? Here, the denominator must be non-zero. And so the domain is all points in three-dimensional space, excluding the plane z equals y. Any point on the plane z equals y will not be allowed. We're going to end with this example. Let's find the level surfaces of this function. This function is of 3 variables, and so if I fix the function to a particular value, that will give me a level surface rather than a level curve. So let's fix f to be equal to w. W is a fixed value. It is a constant value, 1 or 0 or -1. If we do that, then w squared is equal to the radicand. And if we solve for z, we get this. What is this? Remember, w is fixed. So we get a paraboloid with symmetry about the z-axis. And it has a vertex 0, 0, w squared. Here are 4 level surfaces. One for w equals 0, one for w equals 1, 2, and 3. Again, w has to change by just one set value. In this case, a unit of 1 is the change. Let me know if you have any questions on this.